Check, check. Good morning, Jihai. So, Jihai, you may have noticed that we're going to talk about your paper on Friday.
Really?
Yeah, the scales paper. I want to talk about it on Friday. So,
okay. Thank you.
but you know, if you would like to be the one who talks about it, I would be happy for you to do that, or I'm happy to present it. I think so. That's it's up to you, basically.
I think it's better for you to give this talk.
Okay, that's fine, but I will be happy to have you have clarifications and comments for sure. So,
Okay.
yeah,
Okay.
that would be very good.
Okay.
Well, yeah, I don't know yet. I will probably bring a couple of figures from the symmetric instability paper too, since we were talking about the symmetric instabilities today. So,
Okay.
we'll see. Good morning, Rain.
Good morning.
Good morning, Rosa. Good morning, Akash.
Good morning.
Okay, so I was saying to Ming-Chi earlier, I'm sorry, but I messed up the recording on Monday, so there's no recording of what happened on Monday. So that one we just have slides for, but I think I have it working correctly now. So I should be able to upload this one shortly. Can everyone see the slides?
Yes. Yes.
Great. So we will. So today we're going to talk a little bit about the Bachman paper. So on Monday we talked about potential vorticity, and on last Friday we talked about mixed layer eddies, which are a particular kind of submesoscale instability. Symmetric instability is a different kind of submesoscale instability. And so I want to clarify the differences between those, and then we won't really get too much into the details of the parametrization of symmetric instability, except to say that the paper for today presents one. It hasn't actually been checked that carefully. Jin Xuan, who was in the group a few years back, he did his master's thesis on checking the symmetric instability in this versus the high resolution simulations we talked about on Friday. And so we'll have a sense of that, but I think there's a lot more to do there. And so Jihai and Akash both are thinking about this parameterization, how it works, what it does. So I thought it was a useful thing for us to get for their perspective. But I also think that it's kind of a useful continuing illustration of the difference between submesoscales and boundary layer turbulence, in particular the tendency to restratify versus the tendency to mix is also in this case. And so we'll be able to see how that goes. Let's see. So the key distinction here, what we're supposed to be thinking about, this is a really groundbreaking paper from Tom Haney and John Marshall in the late 90s. They opened the door onto a lot of this stuff by revisiting some of the old theory that had been done in the atmosphere by Peter Stone in an oceanic context. And so on the left-hand side, we have what's kind of the classic boundary layer of the ocean vision, which is a lot like the classic Mona-Nabokov boundary layer of the atmosphere that we discussed in Windguard. You might have winds, you might have cooling, you might have heating, but you have a horizontally homogeneous and vertically homogeneous mixed layer above stratification. So when you cool, that mixed layer will get colder and it might entrain, and it's the same thing as the convective boundary layer in the atmosphere, where when you warm at the surface, you might deepen that boundary layer and entrain some of ambient air. And so there's a lot of similarities between this ocean case and the atmospheric case. The big difference being that there's not moisture in the ocean. So there's the classic joke is the ocean is just like the atmosphere except it's dry, which is very silly, except for the fact that that's exactly how the math works out. the moisture equation is what you don't worry about in the ocean. One thing you do worry about in the ocean, though, or you might, is the salinity and freshwater fluxes in addition to the temperature fluxes. We haven't talked a whole lot about that. We'll be able to touch a little bit on that here, and we touched a little bit on that when we talked about the advective versus diffusive fluxes. We'll continue to have that kind of side theme going along. But anyway, so the left-hand side is the classic setup. The right-hand side is what happens if you have a front, a temperature gradient in the horizontal. It's still quite meaningful to have a definition of mixed layer, but now we notice that the mixed layer is really vertically mixed, but not necessarily horizontally mixed. So if you remember back last week when we were talking about the mixed layer eddy case, this happens a lot in the ocean. So in the Haney and Marshall vision, they have stronger cooling on one side and weaker cooling on the other, and that's what's forcing this temperature gradient. So it's cooling faster on one side than the other, it's deepening faster on one side than the other. Entrainment is different here and there. Also, surface cooling is different here and there. But, and they're imagining that this is in a rotating frame of reference. So this front, once it appears, it doesn't just immediately slump over. In fact, it becomes a thermal wind front. So this is a variable mixing way to create a submesoscale front. We saw when we talked about the mixed layer eddies that this kind of front actually also can be forced by the straining between mesoscale eddies, the fronts that get squeezed in between the eddies. And so even if this started this way because of a variation on, say, large scale, like pole to equator temperature difference, pole to equator surface forcing difference, the mesoscale eddies would then make submesoscale fronts by pinching that larger gradient and making it into smaller gradients. So the question, though, is how different are the instabilities of this boundary layer versus the instabilities of this boundary layer? And you would imagine that they're going to be extremely different, because in this case, we might have a horizontally homogeneous but vertically sheared flow, which allows us to have a shear instability that carries horizontal momentum upward and downward. But here we have the potential for other kinds of shear instabilities, because we have both a vertical shear and also potentially lateral gradients in temperature. And so there's lots more interesting stuff here. In addition, the way that we talked about it in WindGuard is when you have a baroclinicity within the boundary layer, you have to be aware of the thermal wind shear that's coming in to compete with the shear that's driven just by the redistribution of momentum by turbulence. So this case on the right-hand side is the much more complicated case, and in many ways this is the essence of submesoscale dynamics, is trying to understand how we think of these fronts. So we talked about the baroclinic instability, which is the sort of quasi-geostrophic-like instability of this kind of frontal structure. Today we're going to talk about symmetric instability, which is another branch, which is kind of like a mixed internal wave geostrophic instability. Okay. So this is the paper. Scott Bachman, as you might know, was one of my PhD students. He now works at NCAR. John Taylor is a fluid dynamicist who's in Cambridge. He's actually the person who I went to visit on my sabbatical a few years back. And then Leif Thomas is, at Stanford, he's one of the key people in submesoscale theory. So we all got together to try and figure out how to write down a parameterization of symmetric instabilities, which John and Leif had been describing how large eddy simulations of symmetric instabilities worked, but hadn't written it down in a parameterization before. And so what Scott and I discussed during my sabbatical, Scott at the time was in Cambridge, was how to do that. So the parameterization of symmetric instability for a resolved front, so that lateral gradient, but within the mixed layer is expected to be resolved, but maybe the instabilities that form off of that are not. That's what this parameterization is meant for. So you might think that this was a parameterization suitable for when you only resolve the mesoscale or when you only resolve the larger features of the submesoscale, but didn't resolve the smaller submesoscale symmetric instabilities. So the parameterization is dependent on external forcing by surface buoyancy loss, so just like the Haney case, and or downfront winds, which we'll see how that works in a second. Both reduce potential vorticity and lead to conditions favorable for SI. The parameterization consists of three parts. The first part is specification of the vertical eddy viscosity. Just like KPP, it needs to vertically mix momentum, but now it's going to be vertically mixing the geostrophic shear, not the just wind-driven shear, which is derived from a specified ageostrophic circulation resulting from the balance of the Coriolis force and the Reynolds momentum flux. So a turbulent Ekman balance is the basic fundamental of that, with the previously proposed vertical structure function for the geostrophic shear production. Okay, so all this is being collected from the literature as to how SI seemed to work. The vertical structure of the eddy viscosity is constructed to extract the mean kinetic energy of the front at a rate consistent with the resolved symmetric instability. Great. The second part of the parameterization represents a near-surface convective layer. So just like we saw in the atmospheric boundary layer where we had a Mononabokov separation between a near-surface shear layer and then a deeper convective layer, in the SI case we have a near-surface convective layer and then a deeper SI layer. So that's the balance of how this works in the symmetric instability case. So we're going to think about how that goes, and that comes into the parameterization in a way we'll see. The second, and then the third part of the parameterization represents diffusive tracer mixing through small-scale shear instabilities in SI. The diabatic vertical component of this diffusivity is said to be proportional to the eddy viscosity using a turbulent Prandtl number, and the along isopycnal tracer mixing is represented by an anisotropic diffusivity tensor. So the anisotropic diffusivity is kind of similar to what we talked about for the mixed layer eddy case, except that there we had a stream function of diffusivity. Here we just have the diffusivity. And then the diabatic part, the part that's mixing across isopycnals, is proportional to the eddy viscosity. So we have two different layers, a convective layer and a deeper SI layer. The shallower layer is diabatic, convective. The deeper layer is adiabatic and has a long isopycnal transport. And then we're going to see how the restratification and extraction of energy sources, how that all works itself out. And then preliminary testing of the parameterization using a set of IDLS models shows the extraction of total energy consistent with SI resolving LES. So we're going to close by just getting to a few of those LES results and starting to see how that goes. Okay, so let's think back to our discussions of instability and stability, because that's part of the game here. So remind ourselves, we talked about the Charney-Stern-Pedlosky conditions for stability. And they are the geostrophic instability. So, but here we mean the instabilities like mixed layer eddies that are the geostrophic branch, the ones that persist in the quasi-geostrophic equations. Those are if only one of the following is true. So if the potential vorticity changes its sign, or if the potential vorticity is opposite sign at the surface, the potential vorticity is the same sign at the bottom, or the shear at the top and the bottom has the same sign. Okay, so in all cases, we're talking about the potential vorticity. So these kind of conditions are possible, but we don't actually, the first three talk about the sign of the potential vorticity gradient, but not the potential vorticity itself. The potential vorticity could be positive, and all of these conditions might still be true. Does that make sense to everyone? Let me say that again more slowly. This is about the sign of the potential vorticity gradient that governs whether geostrophic instability exists or can exist. Gradient, gradient, gradient. But I could have the potential vorticity be positive everywhere and still have this class of instability work. So in a highly stratified flow, you could have all of these be true. We could have the Edie problem, which is stratified top to bottom. We could have the Charney problems, which are based on this. There's lots of instabilities of the geostrophic branch. That's one class of instability of a geostrophically balanced front. The symmetric instability branch is different. The symmetric instability branch occurs only if the PV itself, not the PV gradient, is negative. So this is a stricter criterion than this geostrophic mode piece. This is a little abstract. We're going to come back to this in later, but I want to think about this in a little bit more graphical way that'll help you understand what's going on here. So we're going to get to that. So SI can occur when the sign of the Ertel potential vorticity, this is the way it's written in the paper, is anticyclonic. That is, when Q is the opposite sign of the Coriolis parameter. So FQ is less than 0. That's the Hoskins 74 criteria. Okay. Let's think a little bit about how big the SI are versus, so where you have the geostrophic instabilities, which are the mixed layer eddies in this case, and then we have the SI. How big are the two? So if we assume a geostrophically balanced flow with a buoyancy gradient and the horizontal buoyancy gradient, remember we have to have a horizontal buoyancy gradient in order to have the symmetric instability or the geostrophic instability. We could have a stratification, but we expect the stratification to be relatively low because we're thinking about mixed layer things. So the Richardson number, which is really the kind of a ratio of these two things with a correction of F factor, the Richardson number should be small. And the PV is potentially negative, and we have PV gradients in all cases. The SI growth time scale, T, so the fastest growing mode is the one with the minimum of a time scale, and the horizontal length scale L, so the maximum length scale, the biggest horizontal length scale, the fastest growing time scale are given by these formulas. So let's look at that. Here is H over U. So this is basically the shear, or 1 over the shear. So the bigger the shear in the mix, in that thermal wind shear in the mix layer, the faster the modes grow. The time scale goes down as the shear goes up. Great. Look at this funny combination of the Richardson and 1 minus Richardson. So 1 minus Richardson in the denominator is kind of key here, because it turns out that if the Richardson number is greater than 1, these modes are stabilized. There are no growing modes for Richardson number greater than 1. Richardson in this limit, when we calculate the PV of a front and the Richardson number, the balanced Richardson number of the front, they are actually closely related to one another. So the PV being negative is the same thing for the background flow as the Richardson number being less than 1. So you might worry about what happens when the Richardson number approaches 1 here and this denominator goes to infinity. That's exactly how this mode becomes stabilized as the Richardson number equals 1 is approached. So for the Richardson number for the SI, we're thinking about really unstratified things, really mixed layer things. Small Richardson number, like we had for shear instability, the Richardson number needed to be less than 1/4. Now we're talking about the things in between 1/4 and 1 could still be unstable to SI, even though they would be stable to shear instability. And then here's the maximum of length scale, which has also got this 1 minus Richardson number factor. So they're getting smaller and smaller as we're approaching the Richardson number of 1. They're getting bigger and bigger as the velocity is going up. So this is kind of an interesting combination. But if we plug in some typical scales for U between 1 centimeter a second and 10 centimeters a second, the mixed layer depth between, say, 25 and 100 meters, and the Richardson number in that range between 1/4 and just below 1, which is kind of the sweet spot for SI. The SI time scale ranged from 1 minute to an hour, so really fast, faster than you might expect for something that has to do with Coriolis parameter, much faster than the pendulum day, and length scales of only 50 to 2,500 meters, so much smaller than the mixed layer eddies. So the geostrophic branch, the mixed layer eddies, have a time scale for these same parameters of about 14 to 18 hours, and a length scale of 600 meters to 8 kilometers. So this is about an order of magnitude smaller in length scale and more than an order of magnitude faster in time for the symmetric instability. So if you're looking for a fast-growing thing in the mixed layer, the SI are going to be the fast-growing thing that's going to be dominant on the fast time scales after you have a convective event. Okay, so I'm gonna clarify why convective event is important for their existence. Are there any questions about this stuff right now? Is this coming together for everybody?
Hi, Miller.
Hi, Miller. Oh,
Okay.
Jay, please go ahead.
Okay. I have one question about the criterion for the symmetric instability. The potential vorticity is negative from a background of geostrophic balance, right? From Hoskin's theory.
That's correct.
So, does this criterion is general criterion or just a criterion for the geostrophic background? For example, if we focus on model simulation, for example, just 1 kilometer, there's a geostrophic background. Does this PV negative is still the very accurate criterion for the symmetric instability?
That's an excellent question. I'm going to talk a little bit more about what the PV criterion, how to think about it. But it is the case that if you had an inertial oscillation or an internal wave that was oscillating the shear, you can show that the ageostrophic shear is actually important in this criteria. If you were making it more sheared, less sheared, more sheared, less sheared by having an oscillation in an inertial oscillation, that inertial oscillation would not be affecting the would not be affecting the PV at all, but you can see that can sometimes trigger these instabilities. So it's not, the geostrophic approximation is not the full story for sure. But for this simpler case where we're thinking about this, how to make a criteria for the symmetric instability and to have the kind of pure symmetric instability, not a mixed symmetric inertial instability, we can think of it as a geostrophic background flow.
Okay.
Akash, did you have a question?
No, it's fine.
Okay. So let's think a little bit more about what this about what this potential vorticity criterion actually means by thinking about the potential vorticity in kind of an interesting framing. This is not a way that we've discussed potential vorticity before, but it's equivalent to how we've discussed it before. So it's kind of interesting. So Leif Thomas in this 2017 paper picked up on a thread of how to describe this, which is partly in response to what Jihai just asked about. If we take the classic scenario of a homogeneous uniform stratification, homogeneous in the horizontal, homogeneous in the vertical, these black lines represent the isopycnal surfaces. There's actually another conserved quantity, the absolute momentum. So this is the velocity into the board direction here. So y in this direction, z in this direction, u is directed into the page here. So u minus f times y being the distance in this direction, is another conserved quantity for adiabatic and viscid oscillations in this parameter. So what does that mean? Let's think about if we displace this little blue dot to the right, it would accelerate. As you displace it, this Fy is going up, which means that u must also be going up to keep this absolute momentum from changing, which means that as you displace it, it would start accelerating in the cross-front velocity direction. And then as it would go back like this, coming back across its initial position and overtaking it. So here in the along front velocity, cross front velocity direct plane, what you see is that it would go around in a circle. That's an inertial oscillation. So this conservation of this absolute momentum is one way to think about it what an inertial oscillation is all about. It's about the u, the along front momentum direction, exchanging with f times the displacement. So that thing is oscillating back and forth in this kind of classic setup. If, on the other hand, we put some tilt into the isopycnal surfaces, then we get a thermal wind shear because of the tilting isopycnal surfaces, and that actually makes the absolute momentum surfaces tilt as well. So we get this rather more complicated setup. But if you displace this little ball along an isopycnal, so still conserving its density, it will still oscillate back and forth just on a kind of elliptical trajectory like this, which is what following the consequences of the u minus Fy is in this tilted framing, because now u is a little bit bigger at the top and a little bit smaller at the bottom. So as you oscillate back and forth, the cross-front velocity still goes over the same range that it would have gone before, but the along-front velocity is not as big as it was before. It doesn't visit the same range because it's in a vertical shear as it's going back and forth here. If you displace this little blue dot up and down instead, it would oscillate up and down in just a normal internal gravity wave oscillation. And so almost, I think we went through this in class, but I'm sure that I went through this in pretty much every other class I've taught. So I think everybody has seen that if you go through that game, you get a vertical oscillation where the stratification is the oscillating frequency. The buoyancy frequency, n squared, n is actually the oscillation frequency of that pure vertical displacement. So if we have a pure horizontal displacement in this, we get an inertial oscillation with the frequency f. If we do a vertical, we get an oscillation with a frequency n, and on angles in between, we get some blend of those two. That's the nature of inertia gravity waves, is they are displacements, always stabilized displacements in this kind of setup. If you go into this case where you have the front and also the displacements, it's a little bit more complicated, but this paper from Leaf goes through that case all the way along. Okay, so how does this relate to our sign of the PV? That's a critical key piece. In both of these cases, the PV is positive everywhere in the domain. I can tell you that because these displacements are stable in every orientation under these circumstances. Let's see what it looks like when you go to PV equals 0 and beyond, when PV equals negative. And we'll start to see how these same restoring forces stop restoring in that case. So if we write down F times Q, and we just write out what for this geostrophic front, where that shear is coming from, so du, dy, and then du, dz are the components of the vorticity here. And we've got the F, which is there, and then we're multiplying by F as well. So you can see there's some ingredients. Look, this is the ingredient of thermal wind. This is also an ingredient of thermal wind. So we can, if we plug in for the geostrophic absolute momentum, F minus UGY, we find that the PV can be written like this, where it's the y derivative of the absolute momentum times the z derivative of the buoyancy minus the z derivative of the absolute momentum times the y derivative of the buoyancy. That's interesting. Look, it's like the Jacobian of the absolute momentum and the buoyancy, ddy ddz minus ddz ddy. Or put it another way, if I divide through by bdz, so n squared, and I divide through by the vertical derivative of the absolute momentum, while recognizing that I can't do that if, in this case, the absolute momentum, the vertical has no vertical derivative here. The red lines are, there's no change in m with the vertical, so I have to be in something like this frontal configuration before I can even calculate dmg dz and have it be non-zero. So, but in a front, I've always got this, so I can divide through by that. And now look at what this is. This says the PV divided by these two terms is the horizontal derivative of mg over the vertical derivative of mg, which is the slope ddz over ddy. That's the slope of the red lines. That's what this term is. Minus the slope of the black lines. So the PV is proportional to the difference in slopes between the black lines and the red lines. In particular, if I want to make the PV equal to 0, I can do it by making those two slopes parallel. If I make them parallel, oh, that's in the way, then I get the PV equals 0 because this term is exactly as big as this term, so that equals 0. There's these other scale factors, but the PV itself would be 0 in that case. And now if I keep tilting the momentum surfaces relative to the density surfaces, and I get to this really strong shear front case, where now the momentum surfaces are less steep than the density surfaces, this is where the PV goes negative. So the PV is negative in this case. This is the unstable to SI configuration. This would be neutrally stable to SI. And it's because if we think about, when we pushed it this way, the absolute momentum restored us back. If we pushed it this way, the density restored us back. If we push it this way, the absolute momentum restores us back. If we push it this way, the density restores us back. In this case, if we push it, it doesn't have any restoring force. You would just be neutrally unstable. You could just keep drifting. And in this case, you actually would be unstable. If I push it in this direction, the absolute momentum would restore me back, but it would restore me back to a different location. And then if I pushed across the density surface like that, it would restore me, but it would restore me in this direction. So I would actually be unstable in this configuration. Each perturbation would tend to build, and I would grow, and that's kind of displace me along density, then along momentum, then density, and along momentum. I would ping away rather than being restored back to where I was coming from. So, does that make sense to everyone? The nature of the potential vorticity here that is key for the symmetric instability is the relative slope of the absolute momentum surfaces to the slope of the density surfaces. And so, as our front is getting stronger and stronger, our PV is getting more and more negative because our buoyancy surfaces are getting more and more steep. That's making our shear even stronger through the thermal wind, which is making ourself more and more unstable. Does that make sense to everybody? Sorry, I can't quite see what that says. Can dB dz... Can dB dz, dm dz be very large numbers? So the Q is non-zero even when the right-hand side is small. Okay, let's go back and see what you mean. Actually, the key here is that dm dz could be a very small number, which means that the potential vorticity could be really, really big in magnitude, even when these slope differences were quite modest. So we could have a very large negative PV if either the stratification was low or the absolute momentum was not that steep. So in this case, imagine if we're convecting, cooling at the surface, our isopycnal slopes are getting steeper and steeper because of that cooling. That would be tending to drive dB dz towards 0. And if it was in this configuration, the potential vorticity if it starts out negative, it starts out in this configuration, we'll be getting more and more negative like that. And here's a key point, though, that that Hoskins makes, which is worth talking about. If we're thinking of the convectively stable state, this state up here, the potential vorticity here is always positive. And in fact, that's true for this one as well. Even in the presence of a front, as long as those momentum surfaces are more steep than the buoyancy surfaces, the potential vorticity is still positive. So if we take a bunch of potential vorticity water and move it around and try and concentrate it with things like frontogenesis or instabilities or mesoscale eddies or whatever, we cannot drive the potential vorticity to the opposite sign, because potential vorticity is materially conserved. So if we start out with a positive PV and we just stir that water all we want, can't change the sign of the PV, can't make it negative. We can make its gradients bigger or smaller, and making the gradients bigger or smaller could lead to geostrophic instabilities, but we can't make its sign negative. So if you start with positive PV water, you cannot, through any rearrangement of that positive PV water, end up with a symmetrically unstable condition, symmetric instability, unstable condition. You need to drive the PV negative, which requires a source of PV. So frictional and heating effects are needed to generate symmetric instability to symmetric instability in a previously stable atmosphere or ocean. Okay, so that's part of the parameterization as well. So what we're imagining then is we're imagining a configuration that looks like this. Here are isopycnal surfaces, here's the potential for overturning. We're going to need either convective cooling or winds that are down front, which is in the direction to drive the Ekman transport across, bringing cold water on top of warm water. That is an Ekman buoyancy flux, EBF. One of these features is required in order to drive toward negative PV. If we are warming the surface, we're actually driving towards positive PV. If we are having an upfront wind rather than a downfront wind, we're driving positive PV, not negative PV. So in order to get SI to occur, we need to have a some kind of frictional, like wind, or diabatic, like cooling effect to make the conditions favorable for SI. So this is a different way of thinking of it. So we now touch back to our PV discussion on Monday. We talked about the PV, and we talked about how it has frictional terms and mixing terms and then advective terms. And on Monday, we were really interested in thinking about how we would treat 3D turbulence, and from 3D turbulence, put an eddy viscosity in here or an eddy diffusivity in here, and then think about that as the PV. It doesn't really matter here whether we're talking about the 3D turbulence eddy viscosities or eddy diffusivities or molecular viscosity, molecular diffusivity. We need these terms if we want to drive the PV negative, because the advection of PV, which is the only other thing that can change PV, can't change the sign of the PV. It can just make it converge or diverge like this. So I need those frictional injections, and those frictional injections happen from surface forcing. So if we just rewrite this down here, so here's F dotted into that PV force. So this is FQ. This is the thing that needs to be. This is the forcing that would tend to make your PV negative. F times this, which is on the other side minus sign. So this would be driving PV here toward negative FQ. Is F times this is greater than 0. And what that means is either the buoyancy forcing here is positive, that's the cooling of the surface part, or this crazy combination of the wind stress crossed with the vertical direction, dotted into the horizontal buoyancy gradient. That's complicated, but what it means is that your winds are oriented down your geostrophic front. down front winds tend to make this term positive. So these two terms together will tend to drive toward negative, or anticyclonic, I should say, make F times Q be negative. That's the symmetric instability criterion. Both of these cases are going to tend to drive turbulence, vertical mixing from convective cooling at the surface, or wind-driven shear that's going to make the geostrophic shear production of, here's the Reynolds stress and the horizontal momentum of that front being mixed in the vertical, dotted into the geostrophic shear that's there. That turbulent transport is going to be a positive source of energy in the case where this is where these conditions are holding. So we're connecting together the energy budget and the forcing necessary to get to SI. So SI is not going to occur unless the geostrophic shear production is positive. And in fact, there's going to be so much geostrophic shear production that we're going to see that this term is actually working against the buoyancy production, and we're getting, rather than a sorry, let me take that back. The geostrophic shear production is going to be an important source, but we're also going to need to think about having the buoyancy production in the game as well. Okay, so how do we take all these ideas and convert them into a parameterization? Well, we want to make a parameterization which would represent the following processes. It's going to it'll mix momentum, buoyancy, and tracers when that forcing is greater than 0. It's going to extract energy from the resolved flow by symmetric instability. That's the geostrophic shear production part, and maybe also buoyancy production. We'll see how that goes. It's going to have a long isopycnal dispersion of tracers by symmetric instability. Symmetric instability don't tend to overturn the contours there. Remember we said that in order to get enough energy, enough shear to overturn the isopycnals and cause vertical mixing, we would need a Richardson number less than a quarter. That's the measure of the energy density you need to overturn isopycnals. For SI, they are not necessarily Richardson number less than a quarter. They might be Richardson number, a half or 3/4. So they are going to do mixing along the density surfaces rather than across for at least part of where they are unstable. And so the successful parameterization should also have no effect when the forcing is turned off, when there's not a front, or when the stability criterion is not met, the instability criterion is not met. It should act only in the unstable part of the surface boundary layer. So in the vertical, we'll actually have a negative PV near the surface and then positive PV below. So it should act only where where this condition is satisfied. And then we'll maintain energetically consistent boundary conditions on momentum, buoyancy, and PV. Okay, that's the game. Okay, here's the parameterization. So taking those principles, converting them into equations, how does it work? There's a lot of complexity here. I'm happy to discuss this in greater detail, but basically here is the role that it plays in the momentum equation. There is a viscosity based on the SI. So a vertical viscosity. So this is the U prime W prime contribution. There is a long isopycnal diffusivity, and there is a convective vertical diffusivity. 3 different pieces of the game. Here is what scales for the viscosity. So if that geostrophic shear production is positive and there's a front present, this thing could be a number. It will be faster when there's more geostrophic shear production. It'll be slower when there's less. It'll be faster, interestingly, when the front is weaker in this dimensionless formulation. Interesting. That's the way it works out if you try and get the budgets for the momentum mixing right. Here is the diffusivity. It all is proportional to that. This is the diffusivity that goes into this part, the convective part. There's a diffusivity here and also a convective. I should have said there are 3 different parts for the passive tracers. There's a non-local part, which is like KPP. There's a diffusivity, which is like this. These two are not distinct from each other. Here's the specification of the diffusive part. It's proportional to the viscosity, and it has a complicated scaling which is meant to get the right amount of viscosity and diffusivity relationship. moving on to where this along isopycnal transport comes from. Here is the complicated thing that says it's along isopycnals. That's complicated. But we can look over here. Again, it's just proportional to this geostrophic shear production. And it has a Richardson number scaling as well, which helps you convert to the right amount of mixing. This is maybe the most important part, is there is this shallow convective boundary layer, and then there's the deeper SI layer. In the shallow convective boundary layer, you have two different kinds of geostrophic shear production. There's one part that's from the SI forcing, and another part that's coming from convection. So you put those two together to get more geostrophic shear production in this near surface layer. And then below that near surface layer, you have just this SI production. Below that bigger one, you don't have any SI at all. And at the surface, you go to 0 so that you have a kind of profile specified for the geostrophic shear production, which then through this gives you a profile for viscosity, through this gives you a profile for diffusivity, through this gives you a profile for this along isopycnal diffusivity. So all of these pieces are scaling together based on this kind of thinking. And remember, this is the forcing. So how do we find this shallow convective layer and deep convective layer? It's kind of a complicated thing. The first one is the deep layer is governed by the fact that the PV has to be anticyclonic. So we go to the deepest depth that the PV in bulk is negative, and that sets this H. This is kind of similar to how the KPP scheme uses the Richardson number to find the deepest depth where mixing could be. And then this little h versus the big H is solved by this complicated equation, which basically is telling you when your convective, how strong your convective forcing is, how strong your Ekman buoyancy flux forcing is, versus so when the convective forcing is stronger, when the overturning by Ekman buoyancy flux is stronger, it makes the little h and the big H closer to each other, essentially. When these are relatively weak, you might still have SI because FSI is like that, but this scaling, which is, these end up being, so then you have a case where the geostrophic shear is big and the convective forcing is small. So essentially it's the competition between the geostrophic shear and the convective and Ekman buoyancy flux forcing that's important. Okay. So lots of complexity in how this works out, but this is describing all of the aspects of SI that we think we know. How does it work? So here is 3 different large eddy simulation forcings. This one is kind of pure SI scenario where we have convection at the surface. This one is a different set of settings where we have Ekman buoyancy flux as well as convective forcing, and this one has a different combination which was meant to be quasi-realistic. The red lines here are showing what KPP does, so just 1D mixing without thinking about the front being there at all. The black line is a large eddy simulation resolving symmetric instability, and the blue line is the symmetric instability parameterization. The dashed lines here are showing little h, and the solid lines are showing big H. So as the boundary layer deepens, big H is deeper than the standard KPP boundary layer depth would be. Little h is shallower. So SI is both shallower and deeper at the same time of what regular 1D mixing is predicted to do. That's because of the presence of this horizontal gradient. We have a shallower convective layer because the convection is kind of inhibited by the presence of the shear. You have to, in order to mix in the vertical, you have to interact with the shear production, and that makes the convective depth a little shallower, but the SI effect goes deeper. And it's the same is true here, a little less obviously versus KPP, and then interestingly here, KPP seems to be overestimating the depth that you should go to, and here's the two boundary layer pieces. If you look at profiles of buoyancy production or geostrophic shear production, KPP again in red, two different versions of KPP, is doing a bad job of predicting what the LES does. Whereas the kind of simplified profile with those piecewise linear pieces that I showed before for the convective stuff actually seems to be holding pretty well to match what the profile of buoyancy production, the profile of geostrophic shear production is. We're running out of time, so let me say the last piece is, if you look, just to think about mixing versus restratification, so we know that KPP is always mixing. That's how it's built to work. So the integral of the buoyancy production is actually negative. That's to say that KPP is injecting potential energy through mixing, whereas the SI scheme is doing the opposite. It is actually on net between the surface and this big H, it's actually extracting potential energy. It is re-stratifying the layer. So W prime B prime from top to bottom is actually going the opposite direction. So the energy budget of KPP is backwards. It is injecting energy when the SI and the LES are actually re-stratifying. Similarly, for geostrophic shear production, the KPP scheme is actually predicting too much mixing of the shear. It's actually it's extracting more energy from the shear than the SI and the LES are. So here's the LES and the SI, and they're down here at a much smaller amount of geostrophic shear production. So even though this is the primary energy pathway, this is an order of magnitude smaller, this buoyancy production, than this. KPP is doing work, creating potential energy, and extracting far too much shear in order to do that. And so that has consequences when you look for how fast the shear is mixed, et cetera, et cetera. That's what this scheme does. Are there any questions? I have one point more to make if we don't, or we can have questions on just this. Okay, we'll go for one more point. So remember our frontal circulation from the high resolution simulations of Hamilton? Remember I said that this one was an up front wind and this one was a down front wind? So in fact, we have the conditions here in the down front wind to trigger symmetric instability. We can see the mixed layer eddies here. So we're triggering a geostrophic branch instability. But are there also symmetric instabilities hiding inside of this on a smaller scale? There's no reason why they shouldn't be resolved, no reason why they shouldn't be present. How could we use this understanding of symmetric instability to try and detect whether they're there? Well, one thing that's easy to find here is whether there are regions in this flow where we see a convective boundary layer that's shallower than a potential vorticity boundary layer, the SI layer. So do we find little h and big H in this part of the front? And yes, in fact, we do. If we look for the boundary layer based on temperature, so how deep does uniform temperature go? We get these in the Langmuir case, including Langmuir forcing. And in the case with just winds down here, we find these values, which are kind of, see the temperature along that curly front is maybe in the 15 meter kind of depth range. Whereas if we look for the potential vorticity depth, the depth to which PV is uniform, which is the signature, it's actually where PV is going to be close to zero. This is the signature of SI being unstable deeper all the way down to big H. We find a deeper boundary layer, something like 30, 40 meters. So in that down front wind front, we are actually seeing evidence of there being SI along all of those strong fronts. And this is the difference in boundary layer depths, which is kind of order 35, 20, 30 meters in those deep places. And those places are places where there are large vorticity anomalies, which are consistent with the presence of symmetric instability. So this story says that there is symmetric instability hiding within that downfront wind case. So even though we had focused on the mixed layer eddies in that case, there was also symmetric instability present in that simulation. And you might wonder why there's a difference between Langmuir turbulence case, the case with winds and waves, and the shear turbulence case. And actually, we wondered so much that Sean Haney, who a lot of you met at Ocean Sciences, did his PhD thesis on revisiting all of these instability criteria and doing simulations of symmetric instability in the case where Langmuir is present. And just to show you a quick movie, I'll run this. Here's a front. We're looking from above, and you see that where the fronts are absent, you get Langmuir cells. Where the fronts are present, you get a very different kind of instability, which is definitely not Langmuir, something like a roll vortex. It has different orientation. And so fronts and instabilities, Langmuir instabilities, are definitely interacting. If we look from the side, here we have potential vorticity is positive. Here's one front, here's another front, here's negative potential vorticity over there. And as it evolves, the positive potential vorticity is kind of resorting itself. If we look at for structures and the cross-front velocity, we see Langmuir turbulence developing where the PV is positive, and we see symmetric instability, see like that. Those are symmetric instabilities that are forming where the PV is negative. So the symmetric instability goes much deeper down to big H, which big H here is all the way down here. The Langmuir turbulence is not going as deep. And then here is the evidence of the convective boundary layer, which is a little bit different from the overall big H. So symmetric instability is present in these LES. It's on small scales. It's on a scale intermediate between the Langmuir and boundary layer turbulence scale and the mixed layer eddies. And so it's another complicated part of this story that we need to keep track of. All right. Are there any questions? Or should we wrap up for today? Okay, thanks everybody. So on Friday, we're going to talk about Geha's papers on the size of mixed layer eddies in the world and the size of symmetric instabilities in the world. The link is already up on the page, and we will, hopefully, you'll have a sense of how these eddies change from season to season and region to region. And then next Monday is our last class, and we're just going to sum up everything we've talked about from the whole of the semester. Hopefully bring it together some synthesis and try and get a handle on what everything is about. If people have questions about the final projects or the homeworks or any residual pieces, please come ready with those for Friday or for Monday. And the homework, everybody should have found the key, which I uploaded yesterday morning. And everybody should have your peer review assignments. So we'll get all those homeworks wrapped up. The homework reviews are all wrapped up tomorrow. And then I'll get all the homework grades back to people over the weekend. And then the only thing left will be the final project. All right. Thanks very much, everybody. Have a good couple days, and I'll see you on Friday. We'll talk about Geha's papers.
Thank you.